efforts that we are putting into the spectral element model developed by Naval Research Lab in collaboration with Naval Postgraduate School, where the dynamical core is coming from. Pointer? Yes, by Frank Giraldo, who should be somewhere around. Work is done by myself, Frank, and Jim Doyle. First, a short outlook, a brief introduction to the model, then a summary of past 2D results, and then more detailed discussion of subgrid scale mixing parameterization, and then summary and outlook. I want to emphasize that results presented today are for SE only, although within the NUMA framework, development is going on for both DG and CG, or SE. And that's for NUMA framework. One thing also, this model has its spectral element in both horizontal and vertical. So far, probably you heard about spectral element in horizontal, and then most likely it was finite difference, finite volume in vertical, but this is spectral element in all three dimensions. Okay, a brief introduction. We have our domain, and we decompose it into elements. In this case, it's 20 in horizontal and 10 in vertical. Each element is transformed into a canonical element. Here it is. And then within each element, there are non-uniformly spaced LGL interpolation points, and you can see them. They're bunching together at the element boundaries, and the higher the polynomial order, the more anisotropic they are. In this case, it's for the 10th order. And then we define basis functions on these points. They are Lagrange polynomials, and then we construct our variables by linear combination, just like this: expansion coefficient and basis function. And then we solve the governing equation, and then what you need to remember for the rest of the talk is H is the number of elements, P is polynomial order, and then HP refinement, as was pointed out in a few talks already. If you want to achieve a desired spatial resolution, you can get there by either refining, increasing the number of elements, or increasing your polynomial order, or doing both. And I will show you in a second what I mean by that. Here we go. So let's say on the x-axis is number of elements in horizontal, on the y-axis is polynomial order, and then, for example, you can reach resolution, average or nominal resolution of 1 kilometer by having 10th polynomial order and 24, I can't see from this angle, probably 24 elements, or you can have 4th order and 60 elements. So this phase space, or HP parameter space, in this particular case, defines 91 points, and we carefully mapped it out for both dry and moist idealized cases, because we really didn't know what we were getting into. We just wanted to see how the dynamical core actually performs in the dry case, and then with a simple physical parameterization, how it works in the moist case as well. Okay, now back to model introduction. The model is fully compressible, non-hydrostatic. We're solving for density, velocity, and potential temperature. We use a general time integration scheme that allows explicit and semi-implicit methods. So if lambda is 0, then it's fully explicit. If lambda is 1, then we get semi-implicit. Many of the details were already explained in previous talks. In other form, and these are the coefficients we are using for, in particular, BDF2 scheme. There are many more details. We use Schur complement not to solve for 5 variables, but for 1. Jacobi preconditioner, iterative solver, GMRES, And of course, you'll quickly run out of enough equations for your variables, so you are aliasing, and we use Boyd Van de Ven filter for de-alias that. Okay, so quick summary of 2D idealized cases. First, dry. It's a linear hydrostatic mountain wave, isothermal atmosphere, constant Brand-Vasala frequency. This is the wind speed. This is the main dimensions, 240 kilometers wide, 24 kilometers deep. Mountain, pretty standard, integrated to 12 hours. We have top and lateral sponge layer. And what do we get? So first, what did we calculate? We calculated errors based on the analytic solution for the momentum flux. And on the x-axis, we are plotting normalized L2 error. And on the x-axis is normalized time, and normalized by the model that actually performs the fastest. So let me slowly walk you through. The very top line represents off-the-shelf finite difference model with a similar array of variables. And we can see, by all means, if we focus just on this point, it is by far the fastest, and that's what we normalize it with. What are these green dots, or yellow, or orange and red? In fact, you will remember that I plotted this before. So green lines, green circles represent green lines, so that means exactly the same average or nominal resolution of 3 kilometers. Yellow is for 2, orange is for 1, and red is for 0.5 kilometers. So what are we trying to get out of this plot? If you look at the finite difference, no matter how much resources you throw at it, at some point you cannot get any better result. So it just saturates. So if we define efficacy as accuracy gain over computational cost, then you can see that ideally you would be in the lower left corner, right? So you want very little cost for good accuracy. If you now look at the spectral element results, which are these lower curves, and let's just focus on, and I'm plotting 4th, 6th, 8th, and 10th order. You can see that this is 10th, 8th, 6th, and 4th order. They're kind of like bunched together, but the idea is if you actually happen to have resources and you invest them into your model, and you can run your model, you will get payback. So you can definitely get an order of magnitude increase in accuracy. But at some point, then again, it levels off. Now, why is this leveling off? I know why. It's because we only ran it for 12 hours, so we haven't reached the steady state yet. It's second order, yes.
And do you say it's a co-located point?
It's Arakawa C-grid, yes. Okay. So if you look at the convergence, again, we have a kink here because we hadn't reached the steady state. The finite difference, even though it's leapfrog second order, but as soon as you apply the SLN filter, it effectively becomes first order, and that's what you see. In our cases, the accuracy is definitely determined by the error of the time integration scheme. So it's between second and third order. Okay. Then we felt encouraged, and we felt like, okay, let's do something more, realistic, quote unquote. And we added 3 moisture variables. We put in Kessler type, warm cloud microphysics. We had to add viscosity, constant viscosity. We initialized from standard by means that it appears in literature. Mid-latitude sounding, which has large cape, low-level wind shear. The convection is triggered by warm bubble. Wind integrate to 6 hours. Top sponge, laterally periodic, and just run this movie in the background. White is a cloud outline, and there is rain mixing ratio in the red contours. At the very top is total precipitation accumulation. It starts at 0 and goes down. I just wanted to put as much information as possible on this plot. And at the bottom is just instantaneous rain rate, what you get. So we performed this simulation for all 91 points in our HP parameter space. We carefully mapped it out, and we were happy with the solutions. One thing that we did notice is that there was resolution dependence, but that is actually not something unheard of, unusual, and we attribute it to nonlinear nature of moist dynamics, and we did some spectral calculation, and we can show we have evidence for that. Oh, actually, it's twice up there. Interesting. Okay. Again, a walk through our parameter space. If we fix our resolution at 1 kilometer, which means we are on this orange line, and we go from 4th, 6th, 8th, and 10th order cross section at, I think it's at 1 hour, they look pretty reasonably similar. There should be differences, of course, but they're reasonable. And at the bottom is the total accumulated precipitation. We're looking at the cloud outline and the potential temperature perturbation. And so we were happy with that. Okay, so what do we learn from all our experiments? Suggested polynomial order should be between 4 and 8. Why is that? Why not below 4? Well, because you're getting error because you don't have enough points. Why not more than 8? I think the payoff isn't worth it at this point, at least from our experience. So results were encouraging to press forward, and we started playing with the first obvious physical parameterization, which is the subgrid scale mixing. And I already mentioned before that efficacy actually favors spectral element, because if you have resources, you will get payback. So, and results are published in, actually they're coming out next week or so, October. Okay, subgrid scale mixing. Very simple proof of concept based on Lilis-Magorinsky first order closure, or K theory. It's up here. Notice that Km, or eddy diffusivity, depends on a bunch of parameters. A constant is delta, which I will explain in a second. Deformation, tensor magnitude of, Prandtl number, Richardson number. And then there are a couple of, there is something that immediately pops out, and that is, what is the effective grid scale, or delta, in the case of spectral elements, because we have non-uniformly spaced nodal points. So intuitively you could say, well, it really should vary by node. So for example, if you can imagine a small eddy here, that means mixing should not be very big. Or you could say, it should really be just average over the whole element. And I will show you results, because we tested everything. The other thing is too that the theory is based on isotropic 3D turbulence, but we really are just like a layer of whatever. Usually ratio between the horizontal and vertical resolution is 10 to 1. So if you imagine eddies mixing, they're really like squished. So one thinks that it would be probably prudent to limit them by the vertical spacing. So we could say, what, let's just limit this effective grid scale by delta z, which could be again like node specific or element average. Okay, so test case 1, 2D elevated jet, isentropic, which just makes it easy because all the mixing will be mechanically driven. This is our profile of wind speed, goes to 20 meters per second, and then it smoothly drops. And what do we expect to happen? Well, we expect high momentum to be mixed into regions of low momentum. So mixing term then reduces just to the wind shear, mechanically driven, and we use delta x of 1 kilometer and 100 meters in vertical resolution. And we also, because there is no analytical solution, we actually compare our results to the same finite difference model as before. We keep the same horizontal and vertical resolution. And what do we get? So if we have our delta proportional to the actual grid size, delta x, delta z square root, this is the result. So the initial profile is in gray line, and as the shades are going to darker times, that's how the darker shades, that's how the time is evolving. So yes, indeed, we are mixing high momentum to regions of low momentum. And then again, this is the mixing profile. Red is at the initial time, and then as the simulation continues, we are mixing less and less because we have weaker gradient of momentum. Okay. Right, test case 1. Again, if you limit delta z, it just happens that mixing is smaller, so it's much less vigorous mixing. And then we go to our results with the spectral element model. If delta is based on nodal based, that's how it varies. It's bigger in the center because that's where the spacing is the largest. And you see, we are happy it works. If you limit by nodal space by delta z, it's much smaller. If you limit, if it's element based, then of course it's uniform everywhere. It's big. If it's average vertical spacing limited, it's uniform everywhere too, but it's smaller. And then test case 2D, nonlinear flow, because you want to have some wave breaking. We notice that yes, choice of delta affects mixing coefficient vestibility. So at this point, just focus on the mixing here. It's happening at the leading edge. There is a lot of shear, and then eventually when waves start breaking, mixing happens. Okay, let's move on. HP sensitivity, what happens if we actually play with parameters again, 4th order, 6th order, 8th order, 10th order polynomials, but keep the nominal resolution the same. It looks okay. What I'm plotting is Km in yellow, and it should be noisy because it's calculated in different sense. But if you look in the background, the U prime, blue is negative, red is positive. Fields are very similar. And then sensitivity to how we calculate delta, that's okay as well. 3D case, it works in 3D as well. We want to have a breaking over an oblong ridge. And what do we expect? We expect flow deflection around, flow over with wave breaking, over. So what we see is the isosurface of potential temperature. That's vertical velocity. Blue is negative, red is positive. This is the flow deflection. I'm plotting just the lateral component, V. And of course, what's the most important thing is mixing. So we get mixing. Okay, issues. At this point, we notice that there is actually a limit on Km, which will affect the stability. Unfortunately, we would like to continue with this general approach to the model where we have at least 10 different time integrator schemes. So we need something that's generally applicable to all the schemes to limit Km. In the future, we will switch to the TKE-based turbulent kinetic energy mixing, and we'll continue with parameterizations until we have a complete set to do more realistic simulations. And ideally, we would eventually have an ability to do forecast across scales with static adaptive mesh refinement. And as this session is named towards operation, right? So ideally, we're going to operations too. Okay, thank you.
Very much. Question.
So could you extend this to dynamic adaptivity where you have some error measure that would tell you whether you should be increasing order, maybe based on smoothness or change H?
So I think at this point, I don't think we will go towards changing the polynomial order.
Mm-hmm.
We will definitely change the effective number of elements. If you remember Michal's talk, he was talking about adaptive mesh refinement. He's working on the same model, and he's having its conformal refinement. So effectively, yes, we will be doing H refinement. Yes.
And why don't you think doing dynamic P refinement would be helpful?
At this point, I think
we're looking into it. It's
looking
not.
into
It's
it.
not on the. It's not top on the priority, but we are looking into
Okay.
it. It'll be on the list.
probably a lot of work. Yeah.
Can you change the order in the vertical separately from the horizontal?
That's very high on the things to look into. Yes. Yes.
I was curious about your, in comparing in that mountain wave simulation, you're comparing the errors, as I understood it, against the linear analytic solution for the vertical momentum flux.
Correct.
Correct?
Correct.
And I don't know, from my experience in running mountain wave tests, it seems like the biggest issue to deal with in terms of getting accuracy has more to do with the characteristics of the absorbing layer and the lateral boundary conditions than with the details of the numerics. That the analytic solution assumes that everything is radiating vertically or outwards, and it's never exactly that way. And so I'm wondering how much of this, saturating or the error not decreasing further is just because the way the absorbing layers are configured as opposed to the details of the numerics.
It as well could be. I agree. I have to say that the error calculation is only performed on the inner portion of the domain, away from both all the sponge layers.
Yeah, but with gravity waves, you don't get to get away.
Right.
They
right.
come back.
Yeah, so in your KM analysis for the shear jet, you had rather different results, I think, for the different strategies for choosing delta. And have you thought about trying to use a very high-resolution simulation that would actually capture much more of the turbulence and try to see which strategy was most faithful to producing the correct subgrid scale behavior?
Kind of like an LES approach type, or
Something like that, yeah.
that's the idea. Yeah.
Could you just repeat your conclusions with respect to when you added in the physics and the comparison between the finite difference and the spectral element? How much did the error matter? The fact that if you pay more, you basically get a lower error, but when you add in all the physics, did you see that still?
So if you can tell me of a case that I can calculate L2 error on the analytic solution that has actually any moisture in it, I will be more than glad to calculate it. But I think at this point, how do you know how to calculate the error when you have moisture in it?
By comparing with the truth, maybe?
What is the truth?
Well, if you have observations, then you can...
Oh, yeah, we are far from that. Yes.
That related comment.
Yeah, it does. I was just going to say that you can run like a squall line simulation with a constant viscosity, if you like, and then you can converge that solution. And so, even with the Kessler microphysics, because you don't have length scale dependent coefficients anymore. So, you can get a converged solution to compute errors again.
Oh,
Along that same line, how do you deal with negative water vapor in your physics calculation?
Yes, it's true. Those are dirty details. We definitely have not solved the monotonicity. So at this point, in the Kessler module, any negative values are simply just chopped off.
Okay, thanks very much.